Hi, welcome to another video on AEC and ME series. In this particular video, we will see the 555 monostable multi-operator analysis. This is a circuit diagram of a 555 timer monostable multi-operator. There are some specifications given for this particular circuit. The timing resistor RT is 10 kilo ohm and the timing capacitor is 0.4 microsecond, and this is the trigger signal what we are having. So there is a trigger signal which is high and it is going low, and you can see there is a off time for this trigger signal and there is a total time for this, and we have this VT max, that is maximum voltage of the trigger signal, and minimum voltage of the trigger signal is specified as VT min. So there is a T off which is the off time of the trigger. There is a T which is the time period of the trigger signal, and the task is you are asked to plot the output waveform for the following case of the trigger signal. So let us see how the trigger signal timings and all those stuff. So before that we will just see some details of this 555 timer. So let us go to the circuit diagram analysis. Okay, this is the 555 timer in a stable multi-operator mode. Of course, these are all pin number and pin functions, and pin number 2 is the trigger pin. So as we know that monostable multi-vibrator is one where there is only one stable state for this stable multi-operator, of this monostable multi-operator. There are actually two states of this. So one of the state is 0, other state is 1. So the 0 state, that is when the output voltage is 0, it is now the output voltage is 0 volt. So we call it as stable state. So this is a stable state. Suppose if there is a trigger signal which is more than VTL. So now you can see there is a trigger signal which is at amplitude VCC, which is maybe 5 volt or whatever. Okay, let us take this as 5 volt. If it is 5 volts and if this trigger signal is 5 volts, so meaning you are not applied any trigger. When do we say this mono short is triggered? Means if the trigger voltage goes below VTL, then we say the monostable is triggered. So now we have this as VCC, and at a particular time if it goes less than VTL, then we say the monostable is triggered. It goes to quasi-stable state. So this is your quasi-stable state, which is a temporary state. So this remains in the state of high, which is a quasi-stable state, a temporary state which is other than the stable state. Stable state it is 0, quasi-stable state it is logic high, which is now VCC. It remains there for a predefined time. So this time is decided by the capacitor. So capacitor, initially when the output is in stable state, capacitor voltage will be 0. When the capacitor voltage is 0, it remains in the stable state. As soon as the trigger signal goes below less than VTL, the output goes high. Now capacitor starts charging. So now you can see the capacitors keep charging. So when this capacitors keep charging, when the capacitor voltage reaches VTH, which is a threshold voltage of this. Okay, this is VTH. So once it is VTH, then the quasi-stable ends and output goes to 0 state. That is, again it goes to stable state. It will be again in the stable state as long as you apply, till you apply the trigger signal which is less than VTL. If you are not applying any trigger signal, then output is there in stable state. So again the capacitor charges from 0 to VTH, and once it goes to VTH, this pulse width ends. So this is your pulse width, which depends on the time constant of this charging capacitor, which is proportional to the CT value and the RT value. So RT, CT are nothing but timing capacitor and timing resistor. This CS is a stabilizing capacitor which will hold the voltage at pin number 5 as 2/3 VCC. Now let us see how do we get the expression for this TPW. So as we saw in the previous video, capacitor voltage at any time is given by V final minus V initial e power minus T by RC. This is a very general expression of a capacitor being charged through a, so this is, you can just simply think of it like this. So you have a voltage source, you have a resistor, you have a capacitor here. So this is C, this is R, this is some voltage. So how does this capacitor charges? This is as per this equation. Now we have a similar type of thing. So now this V will be keep on changing depending on the experiment or the application. Now this T, now we are looking at TPW. When time is equal to the pulse width, so what is the capacitor voltage? Vc at TPW will be equal to VTH. It is VTH. This VTH can be 2/3 VCC if you don't have any external voltage. Suppose if you have a switch and connect some external voltage, then VTH becomes external voltage. So that depends on whether you have external voltage at pin number 5 or whether you have 2/3 VCC or whether you have the external voltage. Sorry. Now what is V final? Suppose if the capacitor is allowed to charge till infinite time, this is V final, this is nothing but Vc with T tending to infinity. So what is this Vc? This is actually Vc plus minus, let me write as VCT, capacitor voltage across timing capacitor. So if the capacitor is allowed to charge infinitely, it will go up to VCC. So this is VCC. So what is V initial? That is, it is the capacitor voltage when T is equal to 0 for this pulse width. For this pulse width, the 0th time is the starting point. So at that point, what is the capacitor voltage? It is 0. It is 0 volt. Suppose if you substitute all these parameters, okay, then what is this R? This is a charging resistor. In this case, this capacitor will charge to VCC through this RT. So this R is equal to RT. Now what is C? C is equal to CT. If I substitute all this back to this equation, is it not VTH is equal to VCC minus 0 e power minus T pulse width by RT CT. So if you rearrange this, it is now VTH minus VCC equals minus of VCC e power minus TPW by RT CT. Again slight rearrangement, VCC e power minus T on by RT CT is equal to VCC minus VTH. This is VCC minus VTH. So can I now write it as, so now e power minus T on by RT's, okay, this is not T on, this is actually T pulse width. T pulse width is VCC minus VTH by VCC. So now if I flip this, it is e power T pulse width by RT CT. It is now VCC by VCC minus VTH. So then what is this expression then? Then I can write TPW is equal to RT CT ln of VCC minus VTH. Okay, let me write it again. Expression is TPW is equal to RT CT ln of VCC by VCC minus VTH. Suppose VTH is 2/3 VCC. If it is 2/3 VCC, then what is the expression? This TPW becomes RT CT ln of VCC by VCC minus 2/3 VCC. This is 2/3 VCC. So VCC minus 2/3 VCC will become 1/3 VCC. So it is now RT CT ln of VCC by 1/3 VCC. This will go and this 3 will go up. It is now RT, CT, ln of 3. So ln of 3 is approximately equal to 1.1 RT, CT, this is TPW. This is the expression for the pulse width of this monostable multivibrator for a capacitor to charge from 0 to VTH, provided this voltage is 2/3 VCC. Suppose if this voltage is external voltage, then what will happen is this will become external voltage. Then the equation only changes to, so then what is the equation? So if VTH is equal to V external, so what is TPW? TPW is exactly this, RT CT ln of VCC divided by VCC minus V external, because this was VTH. In place of VTH I will have it as V external. So it is RT CT ln of VCC by VCC minus V external. So it is no more 1.1. So this is 1.1 RT CT if VTH is 2/3 VCC. If VTH is V external, then it is ln of VCC by VCC minus V external. Okay. Now these are all the required things. Let us come to this timing diagram. Now we know that this trigger signal is going low less than VTL for a very small duration, and immediately it goes back to high state. So that is a requirement, meaning this T off should be less than TPW of this monoshot. Suppose if this T off is more than this, the pulse width, then as long as this trigger signal is less than VTL, that long my output voltage will be held at VCC. So the quasi-stable state will not end at TPW, because this has not gone back. So let me just tell you that again. Assume that you have TPW is equal to 1 millisecond. Let us take an example. And T off is equal to 0.2 millisecond, and T of the trigger is 2 millisecond. So what I have, the case is something like this. So you have this is, okay, then what is T on? T on is equal to 1.8 millisecond, correct? So this is T on, this is off for a very small duration, it again goes high, this goes like this. So how much is this? From here to here it is 2 millisecond, that's what is this. From here to here it is 1.8 millisecond, this is your on time. This is how much? This is 0.2 millisecond, that's what is off time. If this is V trigger, this is 5 volt, assume that this is VTL. Now how does my output will look like? My output should look like this, because the pulse width is 1 millisecond. So since I have applied a signal, it is less than VTL only at this point. So till this point output voltage is 0, this is my V0, till it is 0. So once the input goes, when the trigger signal goes below VTL, output goes high. Till how long? Till 1 millisecond, because this is my pulse width. Because you can see this has gone above. So this has gone above. Okay, now this will come to ground, and again it will trigger when this is on. So what is this? This is TPW, which is 1 millisecond. So this is perfectly fine. So this is your capacitor voltage goes here, and it goes up to VTH and then comes down. This again goes up to VTH and comes down. So this is your VTH. This is VTH. Now assume that this, okay, now I am not making this as 0.2 millisecond. If I make, again let us take same TPW is equal to 1 millisecond. Let me take T off is equal to 1.6 millisecond. Again T trigger is 2 millisecond. Then what is T off? Sorry, T on is actually 0.4 millisecond. So as per this, T trigger is 2 millisecond. If it is 1.6, then actually that should be 0.4, and the designed pulse width is 1 millisecond, but T off is 1.6. Let us see how it looks. So what's your trigger? Trigger is actually 0.4 is your on time, 1.6 is your off time. This is again 0.4, 1.6. So this is actually 0.4 millisecond. This is 1.6 millisecond. So this is your VTL. This is VTL. This is V trigger. This is VCC. So let us see how does the output look like. So this is, now output is designed for 1 millisecond. So what will happen now is, now this is my output voltage is 0 because there is no trigger applied till here. Once the trigger signal goes below VTL, output gone high, and this would have come, suppose if this was gone up here, if this was gone up, this would have there up to, assume that this is 1 millisecond, this is 1 millisecond. Now this is not coming down here because this trigger signal is still 0. This is your trigger signal which is still 0, so output extends till this point. So it is going up to, so it is no more 1 millisecond, it's actually 1.6 millisecond. Why it's happening so is, even though the capacitor has reached, so capacitor would have reached VTH by 1 millisecond. Now it is allowed to stretch itself because your trigger signal is not gone high. So since trigger is still less than VTL, output is extended beyond 1 millisecond. Now what is TPW? TPW is 1.6 millisecond. You can see after this, you can see there is one more trigger signal. Assume that, okay, now you have the trigger signal next here. So can you see now the output again comes up? This is your output, this is your pulse width. So here it came down, of course, this came down. As long as this is 0, that long it is high. So then when it goes up, so this again coming down. So when it will again go to quasi-stable state, when the trigger signal goes to less than VTL. So this is not a valid pulse width because I am expecting 1 millisecond, but I am getting 1.6 millisecond. This is because of what? This is because you have a trigger signal whose off time is more than this much. So what is the solution to this? Of course, the important solution is T off, or important requirement is T off should be always less than T pulse width you are looking for. T pulse width you are looking for. So let us consider another case. So now, so let me consider, this is first case where it is fairly the expected one. The pulse width is 1 millisecond and off time is far less than that, and you have a trigger signal. After this comes down to quasi-stable state, you are applying the next trigger signal, then this continues. So this is perfectly fine. So this is also fine, this is also fine. Here this is also not correct. So because of this not correct, this pulse width is also not coming as 1.1 millisecond. Let us see the third case. In the third case, let us still consider TPW as 1 millisecond. Let us take T off as 0.2 millisecond, which is less than the expected pulse width. But let us take this T trigger, okay, T trigger as 0.5 millisecond, meaning within this, okay, let me take it as let us take it as 0.4 millisecond. 0.4 millisecond means, okay, within 1 millisecond I am getting 2 pulses. I am getting 2 pulses. So let me write it. So this is the thing. So what is off time is 0.2, on time is again also 0.2. So do I have something like this? This is 0.2, this is also 0.2, this is 0.2. I am just writing it approximately. So I am getting a pulse, a trigger signal of something like this. So what I have, this is 0.2, this is also 0.2, so that this is 0.4. Can you see this is again another 0.4? Can you see this is another 0.4? Fine. So this is what I'm having. Now let us see what the output is. This is trigger. This is trigger. V-trigger. Fine. So I'm having it as 0.4 millisecond. These are all millisecond. So this is 0.4 millisecond, millisecond, millisecond. This is also millisecond. This is time. And it is VCC, and here you have a VTL. Assume that this is VTL. Now let us see how does the output looks like. This is V0. Now, since you don't have any valid trigger signal here, till your input goes less than VTL, output is 0. Output is 0 here. Now, since it has gone less than VTL, output goes to high, and it should remain as high for what time? Till 1 millisecond. So from here it is 1 millisecond. Can you see this is 0.2, 0.2, 0.2. Now you can see here, from here it is 0.2, 0.4, 0.6. This is 0.8, and this is 1. So here it is 1 millisecond. So till this point, is it 1? Now at this point it sees what the trigger signal. Is the trigger signal high? Since the trigger signal is high, it will come down. It will come down. When it will again go high? It will go here, go high here again. It is interesting to see, once you have a trigger signal going less than VTL, it has triggered, the capacitors keep charging like this. It's going charging up to VTH. At this VTH, so before this trigger signal, can you see you have one more trigger signal here? So even though you have a trigger signal during the quasi-stable state, the mono short output is not affected when you have a trigger signal of low state, when the output is there in quasi-stable state. It will look for the trigger signal only after the pulse width. So you can see after the pulse width, or the trigger signal you have it as high. So as long as it is high, it will not affect your output. Output is immediately coming down. See here, see this trigger signal is not affecting me because this is still there in the charging time, because this has initiated by this trigger. So these trigger signals will not affect my output voltage. So basically what we have to see is, if you are applying a trigger signal before the end of your pulse width, it will not be considered. We call it as non-retriggerable mono short. So this will come if this, can you see this T trigger signal is less than the pulse width? So if you can see this, so is this T of the trigger, is it greater than T of the pulse width? See here, you are getting the next trigger signal after this has ended. But here when you are getting the trigger signal, can you see you are getting the trigger signal repeatedly before this time, before this elapses. So these trigger signals will not be considered in this. So that's what is called as non-retriggerable mono short. Non-retriggerable mono short. So these are the three different cases. And of course, suppose if you have this type of signal where T off is not less than pulse width, we need to have a signal conditioning circuit which should make this trigger signal something like this. So this has gone like this, and if I get a trigger signal something like this, see here, if I get a trigger signal something like this, see now, so this is the output of a signal conditioned trigger. I am not applying the raw trigger signal as it is. I am passing it to a signal conditioning circuit, which results in a signal conditioned waveform. So now see here, is the trigger signal gone less than VTL? And it has gone less than VTL. Can you see it is immediately going to VCC? So this is not staying down for a longer time. So in such case, your output will be 0 initially, and it will go to high state, and it will come back to stable state after 1 millisecond. Can you see this is happening exactly for 1 millisecond? Why it is coming down at 1 millisecond means because my trigger signal is no more 0, it has gone to VCC. So this is the effect of passing the trigger signal through a signal conditioning circuit. Meaning over here, this I am applying the trigger signal as it is. So if I apply this through a signal conditioning circuit, so signal conditioning circuit is this. So I am passing it through a capacitor. There is a resistor connected to VCC and there is a diode connected in this way to this point. I'll say this as RD, this is CD, and this diode. So let me say this as DD. So this is CD, RD and DD will formulate a spikes at this point because of this type of signal, this type of trigger signal. So now what is, so let me just spend some time on this. Assume that you have a circuit like this. This is CD, RD. Assume that you have a trigger signal which is like a 50% duty cycle. Assume that this is 2 millisecond, these are also 2 millisecond. Both are 2 millisecond. So now if this is the input, if you want to see what is the output, so let us assume that RD into CD, the time constant should be far less than 2 millisecond. So let us take this as, let RD into CD is equal to 0.1 millisecond. So if RD CD is equal to 0.1 millisecond, let me assume CD as 0.01 microfarad. So then what is the value of RD? Can I just find out? So what is this? So is it not 0.1 exponential minus 3 divided, sorry, minus 3 divided by 0.01 exponential minus 6. Can you see it is 10K? So this is 10K, this is 0.01 microfarad. If I have this, what I'll get here is, so the output voltage that I'll get here is, so this will go like this and this will go like this and this will go like this. This is the type of waveform we want to get. See now, if this is a 5 volt, this is 5 volt, so then this will come to 5, and when this output changes from 0 to 5, this voltage which was there at 5 will actually go to 10 volt. This will actually go to 10 volt. This is what will happen. Now what I should do now here is, so I should ensure that, see, okay, now let us consider, okay, instead of this type of waveform, usually we'll be applying, we may not be having a DC shifted waveform, this may not be the waveform. Okay, let us assume a square wave, something like this. Let me assume a square wave like this. Now if you consider this as 0 volt, 5 volt and minus 5 volt. Okay, let me not consider this. This is an ideal waveform what we, because when you actually do in the lab, you'll be applying a square wave. If you apply a square wave, okay, when I apply a square wave, if RD CD is equal to 0.01 microfarad and 10K, what I'll get is, you can see this output will be something like this. Can you see? So let me write it in a different color. Can you see this is the output you have? This is the output. Can you see this spikes, whatever your spikes you are getting at this point is around 0 volt. Will it go actually like this? Is it actually around 0? Will it go up to 5? Will it go up to minus 5? Suppose if I apply this to pin number 2 of the trigger signal, can you see the voltage is always 0 except during this time, and it is less than 0 over here. So what does this will make the output of monoshot? Since we know that if the trigger signal voltage, if it is less than VTL, my output voltage is always VCC. So I should avoid the trigger signal to be always at ground. So this is always at ground except during this period. What I should do now, I should clamp this waveform. So I have to clamp this waveform from 0 to a higher voltage. So that can be done by connecting. You can see clamping is required because this is around 0, because you have applied a square wave like this. When you apply a square wave from 0 to phi and minus phi as its amplitude, this is the spikes you are getting. So now these spikes, if you apply to pin number 2 of the trigger signal, because most of the time it is 0 volt, when it is 0 volt, output is always at VCC. So what I will do, I have to clamp this. So clamping is required. Clamping of trigger is essential. Clamping of trigger is essential. How do I clamp it? Instead of grounding this RD, I will connect it to VCC. So this is CD, this is my trigger, it's the same trigger signal. Instead of grounding, what I'll do, I will connect it to, this is RD, I'll connect it to VCC. I'll connect it to VCC, I will see the output voltage here. If, output is, V trigger. So what is the V trigger you have here? You have a V trigger, it is the same waveform. Instead of having this at 0, this will be shifted to, now this is 0, this is now phi. So what you will have? You will have a waveform which is going like this. So this is 0, this is phi, this is now 10 volt. So what you have? You have modified this circuit, you actually flip this. So this you have taken it out and you have connected this to VCC. Instead of grounding this, if you connect it to VCC, instead of around 0, you will be getting it around 5 volts. But this is fine now. So you can see the trigger signal is less than VTL for a very small duration. If you see the output of your this one, so output goes high and then comes down, and again output goes high here and then comes down. So the off time is not there for a longer time. Off time is there for a very small duration. That is, a trigger is less than VTL for a very small duration. But the problem with this is, this spike is going up to 10 volts, which is not an acceptable, not a desirable thing for a circuit which is operating at 5 volts. So what I should do, I have to somehow curtail this. So this should not be going up to 10 volts. How do I do that? How do I just make sure that it is not going above that? So you put a diode here. If I put a diode in this direction, this will restrict the voltage above 5 to only 0.7. So this will not be going up to 10, this will be going up to only 5.7 volt or 5.6 volts. So what will happen to the waveform is, this is 0, this is 5, you will have a spike here, you will have a spike, this will go up to 0, then you can see over here, this is not going up to 10, it will go up to only 0.7 and then it goes here like this. So this is, if this was your waveform, let me write the trigger signal, this is the trigger signal. For this V trigger, I'll get this as pin number 2 voltage after it passes through this trigger signal. So this conditional circuit, when it passes through this conditional circuit, you have a spikes. This is 5 volt, this is hardly 5.7, then it is, this is plus 5.7. So if you use this signal condition circuit there, here, so even though you are applying a square wave need not be 0 to 5, even if it is from 5 to minus 5, you will get spikes. So you will get spikes shifted by 5 volt, you will have it like this. So this will be only 0.7 height, this is going up to 0. So this will help you, even though this T off need not be very small. Even though T off is more, you will generate a spike which will avoid this extension of your pulse width. The pulse width will not be extended here as in the earlier case, because you have generated a spike out of this. spike out of a signal conditioning circuit. So this signal conditioning circuit is nothing but a differentiator clamped to VCC, and that's upper part of the spike is removed by this DD, that diode. Okay, that's what is the entire process. Okay, let me rewrite that. So the trigger signal is passing through a capacitor. There is a diode which is used to clamp the waveform, which is used to take out the positive spike. This RDCD will make this trigger signal like a spike. This is connected to VCC, and you have your pin number 2 going there. This is pin 2, and of course you have this pin number 7, pin number 6, which is what? A capacitor goes here. This is your CT, and you have a RT, and of course this is pin number 4 VCC, sorry, reset. This is pin number 8 VCC. This is the same VCC, you can connect same VCC here. This is pin number 3 output. Pin number 1 is ground. This is either it can be same voltage of 2/3 VCC, or you can use a external voltage. So this is V external, this is 555 timer, this is pin 1. So this is your signal conditioning network, which will make the trigger signal, which is like this, to a waveform which is exactly coming this way. So this will make it this way. So this is the red one is here, the blue one is here, the blue one is here. This is trigger. So what the output? Output will be something like this. So once you get the trigger signal, once the trigger signal goes less than VTL, the output goes to high. There's for a predefined time, and then again goes high once it gets a next trigger signal. This is V0. This is time. That's how I can think of doing it. Okay, let us go back to this and then try to you can see here this is given VT max, VT min. This is the maximum voltage of this. If you can see here, what is this VT min stance is? So it is a threshold voltage minimum. So if the threshold voltage minimum is less than VTL, which is suppose if you consider this as 5 volt, then VTL is 1.66. So this has to be less than 1.66. If this is less than 1.66, then the trigger signal is a valid one. So this is 5, that is 0. Then off time is 0.1 millisecond. Pulse width is given as, okay, not pulse width, the entire T time is given as 10 millisecond. So let me just put this over here one by one. Okay, side by side. Let me just we are asked to actually plot the waveform. So okay, if you can see this, okay, I have written the solution here just to make it speed up. As per this RT, CT and 1.1, because it is 1.1, because I am not using any external voltage, then the pulse width becomes 4.392 millisecond. So this is the first case where you have the what is this? The pulse width is 10 millisecond. Sorry, not the pulse width. The total time of the trigger is 10 millisecond. The off time is 0.1 millisecond. So once it goes to off time, the output is going to high state, and it remains in high state for 4.392 millisecond as per this, and it's coming down. Of course, this has to be a flat. So this is again 0. It goes to again high state, quasi-stable state. It remains in quasi-stable state for this duration, because this is there in this duration because your trigger signal is gone low here, and it is, and this is high. This will no more extend the trigger signal. Let us come to this second case, where in the second case, how much is this? Can you see? This is 1 and it is 1 millisecond, and this is 6 millisecond. So this is 1 millisecond, this is 6 millisecond. So not from here to here, it is 6 millisecond. So naturally, since even though the voltage is 1. Okay, B, let me take, okay, actually this is actually B is 1 volt. So this is not 0, this is 5, but this is 1 volt. When it is 1 volt, is it less than VTL, which is 1.66? So this is a valid trigger signal. How much is this off time? Okay, let me just take one more copy of this. Let me just put it aside. Let me take it again. Okay, I can have one here. Can I open one more? Okay, copy, and let me just paste it somewhere and then open there also. Okay, why did I do that? I just paste it here. Let me open this. This is one, and the other one is here. The other one is here. See, now this is fine. Now this is a B, and this is again B here. Can you see this B? So for B here, it max is 5 volt, the trigger signal max, and trigger signal minimum is 1 volt. Actually this would have been 1, and the off time is 1 millisecond. The total period of the trigger signal is 6 milliseconds. So I am getting the second trigger signal after 6 milliseconds. Because my pulse width is hardly 4.392, by the time your next trigger signal comes, this has elapsed and this is there in the stable state, it again triggers. So this is perfect, even though this is 1 volt, even though this is 1 volt. Then see this is 4 volt, just see here, this is now trigger signal is maximum 4, this is 0 volt, and this is 1 millisecond, this is okay, 2 millisecond. This is 1, this is 2 millisecond. If you see here, this is 1, this is 2, this is 2 millisecond. From here to it is 2 millisecond, and this is again 1 more millisecond. Can you see this is almost 5 millisecond? So even though your pulse width ends here, the output is not coming down to 0 because your trigger signal is still low at the end of the pulse width. So that's why the pulse width is not 4.392 millisecond, because by the time it is 4.392 millisecond, if the output has to come down, but it is seeing a trigger signal which is low. So since it is low, it is now get extended. So this is get extended. So that's why this pulse width is 5 millisecond, even though it is designed for 4.39 millisecond. Because of the timing of this trigger signal, at the end of the pulse width, it is still 0, still it is less than VTL. And again you can see it again triggers when the output, when the trigger signal goes less than VTL. This is again, so this is what is the pulse width supposed to end at 4.392 millisecond. It is not ending, it is extended because the trigger signal is still 0. So this is one interesting thing we should keep it in mind. Okay, see this. The trigger signal is amplitude maximum is 5, but the minimum is 2 volt. So this is 5, this is 2. Since the trigger signal minimum is 2, which is not less than VTL, output is 0. Output is not going to quasi-stable state at all. So output is actually 0 volt. So this is not the case. So output is actually 0 because my trigger signal is not less than VTL. So this is not less than VTL. Then you see E case. In this case also, since the trigger signal minimum is 3 volt, whatever the maximum value, since it is not less than VTL, output is again 0 here. Output is again 0. It's not going to quasi-stable state at all. Then you see this F. In F, we have the maximum is 3, but minimum is 1 volt. So this maximum is fine. As long as this is more than VTL, it is fine. This is less than VTL, this is also fine. What is your off time? Off time is 3 millisecond, this is 8 millisecond. Let us see what happens. Can you see this is 3 millisecond off time? This is actually 1 volt, this is 3 volts. Even though this is 1 and 3, so output is going to quasi-stable state. It's remaining there high for how much? 4.392 millisecond. It comes down and it again goes high after 8 millisecond. That is after you get the next trigger signal. So this is perfectly fine, even though this is 3 and 1 volt. 3 and 1 volt. Let us see this. Now you can see this is 5-0. This is 5 volt and 0 volt. But the off time is, this is actually off time. Off time is 5 millisecond and it is a period of 10 millisecond. Now since the off time is 5 millisecond, which is more than the pulse width, which is 4.392 millisecond, the output is extended till 5 millisecond. So this is how it's happening. Let us see the last one. In this case, output voltage, trigger signal is between 5 and 0. See here, this is between 5 and 0, but the off time is at 6 millisecond and the period is of 12 milliseconds. Since the off time is more than the pulse width and it is not passing through signal conditioning circuit. If it was passed through signal conditioning circuit, then I would have got a pulse width of 4.392 millisecond, whatever the time designed. Since it is not going through the signal conditioning circuit, since it is there up to 6 millisecond less than VTL, so output is also 6 millisecond, even though it is beyond the trigger signal, beyond the pulse width of 4.32 millisecond. And we are asking you to find what is the expression for the pulse width if control voltage is other than 2/3 VCC. So that's what we already discussed here. Suppose if the control voltage, that's what is mentioned here. Suppose if the control voltage is not what VTH, if you have a external voltage, then the expression is RT CT VC ln of VCC by VCC minus V external. So this is the expression. This is actually, let me rewrite that. The expression for the pulse width, in case if you are using an external voltage, if you close the switch, then what is the pulse width expression? TPW is equal to RT CT ln of VCC by VCC minus V external. So this is the expression. Okay, I hope now it's clear. So of course this is very interesting. Even though you have a off time larger one, which will be converted to a spike, and this diode will going to cut off that larger amplitude, and this clamping it to VCC will clamp the entire waveform at VCC. Okay, this will be at 5 volt, this will be at 5 volt, this will be 0, this will be going to the, and most importantly, the RDCD time constant should be far less than this time, this whatever time that you have. Thank you.